Okay, composite transformations. So here we have a line segment with vertices 2, 1, and 1, 3, reflected over y equals square root of 3x, and then rotated clockwise by pi over 3 about 0, 0. So my point matrix is going to be this. It must be multiplied first by the transition matrix for that. I'm going to do a different color. So this one effectively has a slope of rise over run square root of 3 over 1. That's a 2. This is a 60-degree angle. So it uses the matrix. I'm going to double check my formula packet, but I think it's cosine 2 theta. Yes. Cosine of 120, sine of 120, sine of 120, negatives. Sine. So
Is it?
well, that's 2 pi over 3 is the angle, but the cosine of 120 is negative half. The sine of 120 is square root of 3 over 2. And yes, having the unit circle memorized makes this just go faster. You certainly could use a calculator, though.
My calculator only gives me super decimals though, so I don't realize it's like square root of 2.
Oh, well, let's change the mode on that because that can be changed.
Well, sometimes it will use fraction and then you have to get the decimal.
So there's a way to do that. It's very easy. Oh, so the next one, it doesn't usually, if it's in the right mode, it doesn't, is going to use this one. So rotated clockwise. So my angle is going to be negative pi over 3. And I don't remember what that one is. So I look at my formula packet. Clockwise. Well, I'll just use the anti-clockwise. I can use, yeah.
Just subtract from 360.
Or you can use the clockwise one. I just don't use that. To just do the angle, negative angle, I kind of agree with that. Use the negative angle. You can, they're both there, but I mostly just don't know why they didn't just do it once. Yeah. There's like, I think mostly I rage that they don't put enough other ones in here, and they put that in twice. So cosine of negative pi over 3 is 1/2. Sine of negative pi over 3 is negative square root of 3 over 2. And then the negative makes it positive. No negatives there. So I have this. And there's my transition matrices all set up. It asks me to write down the matrices for F and T. F represents the reflection, T represents the rotation. So T is purple. And F is this blue. I just changed the color. Why didn't it work? So then it wants us to multiply these together into a single one. I do not feel like doing that by hand.
Those are T, right?
And it needs to be in that order to be F followed by T. It has to work right to left. Yes.
I did one of those wrong.
And then you go, oh, that doesn't work out. So yeah, well, and if you're applying the transformations first to the points, you have to work the ones closest to it. Yes. Yes, translations just add to the end. But so we're going to go to the calculator. I guess I need to add a calculator screen to this. And I'm going to type my two matrices. Wish they weren't written in the same spot, but they're both 2x2s. And this is just a little tedious typing it, but way easier than doing it by hand. And I'm just using 0.5s as all my halves. And wow, that didn't change much at all. So the 0.866 is square root of 3 divided by 2. I'm surprised it didn't give me that as a fraction. So now it wants that multiplied by the point matrix. So I'm just going to hit times and default to that last matrix. I suppose I could have stored it if I wanted, but oops, that's a 1. This is also supposed to be a 1. And I get those points. And yes, that matches up with the answer key. An affine transformation considers it applied in a sequence. So you first multiply the point xy by the transformation matrix ABCD, and then do a translation vector. In linear algebra, these transformations are called affine transformations. All points, straight lines, and planes still exist, but the image may be enlarged and be in a different position, and any angles may have changed depending on it. Uh-huh. Linear algebra is essentially matrix algebra.
So like this part.
This is part of linear algebra. We are doing linear algebra. Usually linear algebra also involves doing proofs with this. That's the hard part that's rough. So the Mandelbrot set, watch this video later. The Mandelbrot set is very cool. And it involves fractals. Fractals are infinitely complex things. So we'll watch this after this is done. That would be, yeah, I think that one could be very difficult.
Yeah.
So here's the thing. An image is first transformed by an enlargement with scale factor 2, followed by an anti-clockwise rotation of 180 about the origin. Finally, it is translated by the vector 1, 1. So they want it to be in this form: x prime y prime equals a b c d x y plus ef. Find the 2 by 2 matrix and the 2 representing the overall transformation. So first, an enlargement of 2. So we're going to go take a look at the enlargement matrix. I think it's 2, 1, 1. 2. No, 2, 0, 0, 2. And that one has to be on the inside. And then anti-clockwise rotation of 180. So there's my scale factor of 2. Anti-clockwise rotation of 180. That one, let's take a look. Cosine theta, negative sine theta, cosine theta.
I don't know why that's like this kind of makes more sense to me.
This So cosine 180 is negative 1, sine 180 is 0. I'm just going to multiply these by hand. Negative 2, yeah. Um, row 2 times column 1 is 0. And that's our transformation matrix. Yeah, when they're simple ones, it takes us long. With the square root of 3 over 2s, I thought it was faster.
I can't do that without you. Well, I just can't.
If you have time, it's always good to check typing them into the calculator. So that's the overall transformation matrix here in red. Hence find the image of 3, negative 3. Oh, and I need finally is translated by the vector 1, 1. Okay, so my 2 by 1 is 1, 1. So my overall transformation, so first thing I'm going to do is multiply. Row 1 times column 1 is negative 6. Row 1 times column 2 is also negative 6. Mhm. Negative 5 set there. How'd they get positive 6? Oh, I missed writing a negative here. I felt like there was something wrong there. This becomes positive 6. and that becomes 7. So very important not to miss writing negatives.
Oh, I'm aware. After the two meet, only lost points for getting the signs of twos are wrong. Only twos.
Hmm. Okay, so triangle here is transformed by the matrix this. Put the triangle image into the coordinate plane. Find the area of the triangle. One, one, 1, 2. Wait, 1, 2 is here. 2, 3 is here. So here's my triangle. It has a base of 1, and I'm going to call this base this height. Actually, I'll call this base this height. It has a base of 1 and a height of 1. So this has an area of 1/2. Find the area of the image triangle. I don't feel like multiplying that by hand right now, so I'm going to stick it in my calculator.
Negative one, negative one, 1.
Times my points were, well, I gotta get rows is 2. 1, 1, 2, 1, 2, 3. And so we get this triangle, which we'll graph in a different color. -2, -3. A prime, -3, +1, -5, C prime. So now I have a base of 2 and a height of 4. Area is 1/2 base times height, so it's 4. So the area grew by 4. It asks me to find the determinant of this matrix. Remember, the determinant is AD minus BC.
On one of the questions, I can find a determinant of the 2 by 3 or something. Because I had to look it up how to do it.
2 by 3. You can't find the determinant of a 2 by 3 by 3 by 3. If you need to find the determinant of a 3 by 3, your calculator can do determinants. So this is -1 minus 1. The area, the image triangle. I feel like there's something wrong with one of these.
X minus x1 times y1 minus
So I think you were supposed to just subtract those to get a single value. But something went wrong in my actual transformation matrix. That was supposed to be 1. Oh, -1 minus 1 is not 0, it's -2. What went wrong in the calculator? This was supposed to be 1, 2. Okay, well, I guess when you type in the points wrong to the calculator, you get a wrong image, and thus a wrong area for it. If I type in the points correctly, I get the correct image here, which shows there's the transformation. It has an area of 1. That area of 1 also helps if I can subtract, right? -1 minus 1 isn't 0, it's -2. I knew something was wrong. So there's this nice little property that the determinant is -2. The area is then going to times by the determinant or be double. You can ignore the negative signs because the areas are negative. They're never negative. Half times 2 is 1. So that's a great little property. Hint, remember that for your test. Times the area gives you the transformed area. So they don't even have to tell you the area or the transformation matrix. They can just tell you the area. So an object has area 3 is transformed by this. What's the area of it? So we'll find the determinant. 2 times 1 minus -2 times 1 of the transformation matrix. Not the determinant of the new matrix or the determinant of the point matrix.
Yeah.
The determinant of the transformation. Transition matrix is something different. So what's the area? This was 3 multiplied by 4, it's 12. So example 3, we have these vertices. And we have the original. It says find the transformation matrix that transforms this. Um, so this one feels like it's easier to do the area first. Maybe not. That's not an easy triangle to do area of. So if we want to find the transformation matrix, we know that it's T times the original point matrix, which is 1, 0, 0, 1, 0, 0 equals yeah, I started with A, so -5, 1, -2, 3, 0, 0. And I think I can actually just drop 0, 0 because that one's not moving. Because otherwise I can't inverse this. I can't inverse the 2 by 3 to solve this.
No worry about that.
So I need to do the inverse of this. And that'll give me my transformation matrix. So
Inverse.
switch A and D and divide by the determinant. And negate B and C. I think that's if you look in your formula packet, I think that is in the the one section.
Yeah.
Determinant of a 2 by 2 inverse dA 1 over determinant dA negative B negative C. But that feature will not be taken away from your calculator.
What about the variables? Like
Yes. -5, -2, 3 times. So yes, get used to using the formula packet. It has helpful information, especially in these matrix things. Do that -1. And my transformation matrix, I guess, is -5, -2, 1, 3. The area then of the large one, the area of the small one, -5, -2, 1, 3. So this one is my area. My small one has an area of 1/2. I think that's right. I'm going to double check that. Yes, that is the correct matrix. So if I want the area, -15 AD minus -2 times 1, that's -13. 13 times 1/2 is 13 over 2. Or 6.5. And that is correct. Again, this whole section on matrix transformations is not that hard if you keep your formula packet handy and understand how to use them. Okay, that is the end of this lesson.